The next speaker is Robert Spragg, the Materials Research Engineer with FHWA Turner Fairbank Research Center, with his presentation on maintenance and repair of bridge infrastructure using ultra-high performance concrete.
All right, well, good afternoon, everybody. Thanks for having me out here. So I'm looking forward to sharing a little bit about what we're doing with ultra-high performance concrete and bridge rehabilitation and maintenance activities. But just to start off a little bit, here's some pictures of what we're going to talk about, or some technologies. We're going to show some applications. So if you have some bridge inventory or things in your bridge inventory that look like this, this presentation might be interesting to you. Just a quick overview, we're going to talk about what is UHPC really quickly. We're going to talk about how it's been used in some particular applications. We're going to delve into some specific applications with some pictures, and then talk about resources if you have questions of who you can contact that can help you. So UHPC is made with traditional constituent materials, ordinary Portland cement, some supplementary materials, fine sand and fillers, water, admixtures. Most of this typically comes in a prepackaged blend from a material supplier. It will have some kind of optimized particle packing, so it's not just, you put all this material into a bag and sell it. There is some development that goes into making sure that this is an effective material. It is available from a wide range of commercial suppliers, so this is not something that you would have to make yourself, or that you would have to contract with a local university to. I mean, there are people that have, but you wouldn't have to develop your own mix. There are commercially available mixtures. Here are some typical price points of these. So these are material costs. These are not necessarily bid line item values. So I'll caution you, if you look at a prior contract, or if you talk with someone that has used this material on a prior contract, they'll typically say, oh yeah, but the bid line item was very high. Sometimes that includes quality control, mobilization and stuff like that. But from a materials point of view, it's very similar price points to materials of other classes. So some general properties of UHPC. I know this is a text-heavy slide, but specifically we're going to stick to the bulleted, or the bolded items, which make UHPC a advantageous material to use in the applications we're going to talk about today. The high compressive strength, the high sustained tensile strength, and the good bonding behavior, and then engineered flow properties. And what I mean by engineered flow properties is this video here. So depending if you want your material to be self-consolidating, that's an option, or if you want a material that only moves when you provide some external energy or some kind of vibration, let's say you're doing a deck overlay that has some kind of cross elevation to it or cross slope, that's an option too. Mechanical properties are pretty self-explanatory. Higher compressive strength of around 21,000 PSI, sustained tensile strength, which means it's able to reach a value of around 700 PSI, and then able to sustain that over a large range of deformation. So where has UHPC been used in projects? I was actually talking to some people yesterday. They've used some UHPC. They show up on the map here. They would have questionable whether that was a successful project or not. But it has been used in around 200 projects across the United States. But when we look at new construction versus repair, there's a lot less projects where it has been used in repair applications. So our presentation today, or my presentation today, is going to focus on repair applications of this material. So I will say that just because it's unique does not mean it's useful. So take in what I'm sharing with a little bit of a grain of salt. It might not be the solution that is the best for you, but it is a potential solution. Another way that you could look at it is it might be a new way of doing things. So we're going to go through this list of potential solutions. In interest of time, I'm not going to really go behind or go with the design methodology or things like that. So if you have any particular questions, you can feel free to contact me or someone else on the project team. Contact information is at the end of the slides. So the first application is looking at pore consolidation around the midspan of a box girder. Here, this was formed up with plywood, and then UHPC was kind of poured in here. The benefit here is that you have good bonds, so you wouldn't necessarily have to try and get in there and roughen your surface or anything like that. So the UHPC would provide good continuity there. And then it also would flow very well, so you wouldn't have to worry about trying to provide some external vibration or anything like that to get consolidation. Another repair technique is looking at adjacent slab beams. So here we have slab beams that had an asphalt overlay, and then there was reflective cracking in the asphalt overlay. That's this picture here on the left. So what they did is they took the design, they They cut out this damaged region and then poured UHPC back in this region to prevent that differential movement causing reflective cracking in the asphalt overlay. So this is what it actually looked like. So they took the overlay off, put the UHPC here between these joints to prevent that differential movement. Bridge deck overlays are another common application of UHPC. This technology has been pioneered in Europe, with probably been used on over 30 bridges. One thing that I'll say is that Europe tends to have some strengthening along with their typical application, whereas most applications in the United States have not necessarily focused on strengthening, but just providing a durable surface on top. So this picture here is from the Chillon Viaduct in Switzerland. That's kind of the popular one. Here's a cross-section of what that bridge looks like. It's very slender looking to me. So they put this UHPC overlay on the top to actually provide additional strengthening mechanisms. But the interesting thing about that is that they hydrodemolitioned this deck. They did put some additional reinforcement down, and then their placement machine was kind of like a slip-form paver is what it looked like. So they would actually take their UHPC and drop it in this end. Let me skip the laser pointer. They would drop it in this end, and then it would kind of move it across and consolidate and move it at the same time. In the U.S., our applications have not been as high-tech as that. So this is a local agency bridge in Iowa that had an overlay put on the top of it. You can see that the deck does have some damage. This is a very common sight, I think, for a lot of bridges. But basically, they formed up with just plywood, or not plywood, but strips of wood, and then would pour the UHPC on the top and consolidate it. So you would just buggy it and then also have this vibrating screed that they would just pull across the top of it. And this is what the final product looked like. So they did hydrodemolition the deck, and then they put the overlay on top, and then they diamond ground it to make this provide a wearing surface. Another application is looking at expansion joints, or more aptly eliminating your expansion joints using a link slab. So traditional applications of a link slab would take out that joint and then put in something that is able to sustain those movements, so something that has a little bit more ductility than a typical concrete. Traditionally, that would have to be relatively large, so around 20 feet wide. That's this traditional example here. When we move to UHPC, that becomes a little bit smaller, so we're able to make that about a 2-foot wide joint. It doesn't even have to necessarily be full depth, but it gets away from that joint that causes leaking on top of your piers. And this is an example of what it looks like on a project out of New York. So this is a UHPC link slab. You probably wouldn't even notice it was there unless you were looking for it, but it does help keep this parts of the connection and everything dry. Another application is looking at repair of corroded beam ends. So typically you'll have corrosion that causes a section loss down here. One particular application is applying shear studs and then forming up this area around the corroded end of the beam, and then casting UHPC in there, and that provides alternative load paths for your loads. This is what a picture actually looks like. So this is on an underside of a bridge, I think out of Rhode Island. So here we see this is the damaged end of the beam, or the corroded end of the beam. Shear studs were applied, and then finally, lighting is a little bit difficult here, but you can see that that panel is there, right there at the end of your beam. All right, so these next couple examples are kind of you could call them a little bit loopy, right? So these connection plates, when there is loading on your diaphragm, or when maybe this is holding a sign or something like that, you could get fatigue cracks that happen here at the top of your connection plate. We're looking at ways to strengthen those or provide some kind of a repair technique. One particular example, you could use a stiffening angle, but the challenge is that then you have to kind of come through the top of your deck to get to your top flange to bolt on those, which could be a little bit difficult depending on where you're at. One of the ways that we looked at that was we created these damaged samples in our lab with these fatigue cracks. And then the repair technique that we're going to do is looking at how we can use UHPC stiffening blocks with these shear studs that we shoot onto the top flange and then also onto the web. Okay, so I think this is the last application. This is looking at strengthening of riveted Thru-Girders. So these are built-up sections or built-up plate girders. And really we're looking at using a combination of post-tensioning rods and UHPC toppers to increase the capacity, provide some stress reduction, enhance structural efficiency. You would cast UHPC on the top with, form it up, and then also you were post-tensioning on the bottom that you would encase in UHPC. And these are some samples that we actually built in our lab and tested, or we are going to test here shortly. You can see the topper on the top here there are shear studs in there, and then the post-tensioning rods on the bottom. If you can see them, these, I guess, along the length of the beam. I guess that was relatively quick, so sorry about that. But if you like some of these things that you see, if you could think that these might be able to be used on some projects, or you would have an interest in talking about them, you can check out our project website. You could also Google it. Hopefully we're working on some design guidance that we're able to release here in the upcoming, hopefully next year. If you have a particular application and you think this might help you out, feel free to reach out and we can work with you.
I just was wondering about gusset plates on historic bridges. If they're, taking out a gusset plate is not an easy thing to do, but we're doing it on one, but it's always a thought. Can you replace it with a block of UHPC and handle the same forces?
That's a great idea. I think one of the benefits of UHPC is that if you could form it up, you could kind of do a lot of unique things with it, so that is a potential application, yeah. The question is using UHPC for headers on expansion joints. That has been an application that they have looked at. There was actually a bridge that I toured in New York where they were doing that, so that is another option.
The fiber, the steel fiber, if we go into Buy America Steel, is that available?
That's the popular question. So the question is whether steel fibers are available. So so for those that are in the know, you understand the question. But for those of you that don't, the main question here is these steel fibers are not traditional steel fibers. They're very small. So 1/100 of an inch in diameter and a 1/2 inch long. That's not a very common steel fiber, especially in traditional concrete, because the aggregate size is relatively large. The producer of these fibers has stopped producing them in the United States, which then doesn't satisfy the requirement of you have to buy American steel products. But there are some manufacturers that are trying to get into the market, and there's also some groups that are looking at potential waivers. That's certainly on many people's radar. I have heard from a couple UHPC suppliers that they have enough of this stockpiled for a foreseeable amount of time. Ask me next year. They do offer waivers. There was actually an email that was sent out last week, but there was like one waiver granted last year. Probably not.
You're applying this to structural steel. It looked like you needed studs in all cases. Do you have to have studs, or can you get decent bond behavior with just corrosion, surface imperfections if you get down to nice, clean steel?
Sure. In most of our applications, we have utilized studs. There is some bonding that happens, but I would say, yeah, you would probably need studs, which I know that makes it a little bit challenging. In some of these corroded beam ends, there's not a lot of good material to put your studs onto, which is another challenge.
Who besides Lafarge is supplying and supporting UHPC? Besides
one particular material supplier, are there any others? So there are probably about 4 or 5 material suppliers that we work with, commercially available materials that you could call them up and they could deliver it probably sometime this week or next week. But then there are also a lot of proprietary groups that are working on helping people develop their own mixtures and things like that too. So there are a couple suppliers. I'm not sure I can say all their names, but I can chat with you afterwards and tell you some people. I'm certain I would forget someone and then I could get in trouble, I guess. Yeah, so the question is the steel fibers. That's the big sticking point with some of these materials. So in some applications, we're looking at using non-metallic fibers. In other applications, the fibers that are being produced are a little bit different than the ones that have traditionally been used. So we're looking to see if they provide the same level of performance. But then there's also suppliers that are saying that they would start producing these fibers if there was a market.
How do you control that at the job site they don't add more water than it is necessary? Because I presume that if the amount of water is wrong, all the performance properties goes down.
It does need a lot of quality control with it. So that's typically why, if you look at, that's the thing that I mentioned about being careful about looking at prior bid prices, because a lot of those bid prices will include quality control from the supplier, because they realize that there is some sensitivity to these materials, so they typically send out their own people and things like that. So, but that is, if you use this on a project, there is you have to be a little bit careful. Great, well, thank you very much.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.